Welcome to The Explainer. Today, we're embarking on a seriously fascinating journey into the highly dynamic, almost invisible world of synchronous generators. We aren't just looking at how these massive machines generate power. We're actually going to slow down time to understand their absolute most extreme behavior.
So, think about that for a second. What actually happens inside a generator the very millisecond a short circuit occurs? On an offshore platform, a catastrophic power fault isn't just a minor inconvenience, it is a massive, critical danger. Understanding the physics of that exact millisecond is absolutely foundational to designing safe, reliable power systems. And hey, for the graduate engineers watching, don't worry, we're going to build this step by step, taking you straight from the physical hardware all the way up to the practical fault calculations you'll be using out in the field.
Here's our roadmap for today. 1. Inside the synchronous machine. 2. The 3 reactances. 3. Anatomy of a fault. And 4. Calculating the impact. Let's get right into it.
Section 1. Inside the synchronous machine. Every single watt of electricity on your offshore platform, it starts right here. Notice the fundamental relationship. You've got a spinning rotor heavily highlighted with its field winding, and it's surrounded by a stationary stator holding the 3-phase windings. It's inside this tiny, crucial air gap between the two where the real magnetic magic happens.
Now, as that rotor spins, the magnetic circuit it creates isn't just perfectly uniform. When the rotor pole axis perfectly aligns with the stator coils, we call that the direct axis, or D-axis. The magnetic reluctance here is at its absolute minimum. Conversely, when the rotor is at right angles to the stator coils, it faces the widest part of the air gap. This is the quadrature axis, or Q-axis, and the magnetic reluctance here hits its maximum. This steady-state shifting of magnetic reluctance is the baseline of our machine. But what happens when things go wrong? Let's dive into how the mathematical models dramatically shift over time.
Section 2, the 3 reactances. Okay, let's dive into this.
Imagine a short circuit hits. If we plot the machine's response curve on a timeline, it's actually brilliant how it behaves. Looking at the time after the fault, 3 distinct horizontal lines emerge. In the very first instant, from 0 to 0.1 seconds, we are at the lowest reactance level, called the subtransient reactance, denoted as XD double prime. Moving forward from 0.1 to 3 seconds, the reactance rises to the middle level, the transient reactance, or XD prime. And finally, after 3 seconds, the machine settles into the highest level, the steady-state synchronous reactance, which is simply XD. What's truly fascinating here is how that exact physical timing directly dictates the mathematical value we absolutely must use for our engineering studies. Just look at the typical values. In that subtransient time frame, the reactance drops dangerously low, typically between 0.10 and 0.20 per unit. Because this governs the highest surge of current, XD double prime is exactly what we use for our initial peak fault calculations. As time goes on, we use the transient value for stability studies and the steady-state value, which is much higher at 0.8 to 1.2 per unit for your standard load flow analysis.
Mathematically, this subtransient reactance comes from the exact physical path the surge takes. If you trace the equivalent circuit as it builds, the surge hits the armature leakage, XA, right in series. It then splits into a parallel bottleneck between the field winding, XF, and the damper winding, XKD, shown right there as parallel branches. Following that circuit path gives us our vital XD double prime approximation. But why do those specific damper windings matter so much in that first fraction of a second? Let's zoom right into the physical air gap to find out.
Section 3. Anatomy of a fault.
When the short circuit occurs, the stator current just suddenly skyrockets. The inciting incident here is that this massive additional flux produced by the stator is violently forced into a region consisting of just the air and the surface of the rotor poles. Because it hasn't fully penetrated the rotor core yet, this is a very high reluctance condition. And in electrical machines, a high reluctance condition is exactly what gives rise to those extremely low subtransient reactance values we just saw. So, the crucial point is how the machine physically fights back. As that sudden flux tries to penetrate the rotor poles, it encounters the damper bars embedded in the pole faces. Through the process of transformer induction, this flux induces massive currents inside these copper bars. They essentially act just like a squirrel cage induction motor during a sudden speed change. These induced currents set up an opposing flux to repel the stator flux and maintain constant flux linkages. Honestly, these damper bars are your machine's heroic first line of physical defense. Now, let's see how this all builds into real-world engineering.
Section 4. Calculating the impact. Let's move to and see how this builds.
When predicting catastrophic fault currents for your switchgear, to keep an offshore rig actually safe, this is your exact methodology. Step 1. You calculate the RMS symmetrical subtransient current, and as we learned, you must use XD double prime for this. Step 2. You have to account for an accompanying DC offset by applying a doubling factor. And finally, step 3. This combined calculation gives you the peak asymmetrical duty. That is the absolute worst-case current your equipment must withstand in that very first cycle.
Let's look a little closer at that current doubling effect. In differential equations involving resistance and inductance, a DC component naturally accompanies the symmetrical AC component. The magnitude of this DC component is also determined by XD double prime. But how long does it actually last? Well, its decay is governed by the armature time constant TA. This time constant is a direct function of the subtransient reactance and the armature winding resistance. If your generator has a high XT double prime and very low armature resistance, watch out. That DC component is going to hang around, creating a massive, sustained current spike. 2.848. If you are calculating a fault and only have the subtransient reactance with an unknown resistance, you assume the X to R ratio is infinity to be perfectly safe. Under that assumption, you apply a doubling factor of 2.848. You multiply your symmetrical fault current by 1.414 and then by 2.848. That number represents full current doubling, and it emphasizes just how dangerously high, we're talking almost 3 times the standard peak, these fault currents can spike in that very first cycle. No joke.
So, I want to leave you with this provocative thought. How will this catastrophic peak asymmetrical duty alter your next switchgear sizing decision? Because when you're designing hardware for an offshore platform, you aren't just designing for normal, everyday operation. You are designing to survive the subtransient millisecond. Thank you so much for joining me on this explainer. Keep learning, keep analyzing, and I'll catch you next time.